All right, everybody, welcome back to the IDE Lunchtime Seminar for 2021. It's great to be here with some of the usual suspects, as well as Johan Ugander from Stanford, who has just been doing amazing, fantastic work across so many different dimensions. You know, just from on a personal note, I've never worked with Johan, but I've read most of his papers, and he is a scholar who whose papers I thoroughly enjoy and look forward to, you know, like receiving and reading. Like it's kind of like getting, you know, like your favorite publication in the mail, and you can't wait to kind of like see what's in there. I don't say that about a lot of people, honestly, but it never disappoints. And so today's going to talk about graph cluster randomization, of which he is one of the leading sort of creators of this method and this theory, which has become, in my mind, the leading approach to large-scale digital experimentation that accounts for and measures network effects in the presence of interference in a large-scale experiment. And I'm sure he's going to tell us all about the technical details and any advances that we have seen recently. So Johan, take it over. Just a little bit of ground rules. I'll be listening, but I'll probably turn my video off. Folks may interrupt, you know, with questions in the chat. That is, you'll run the show in terms of whether you want to stop and answer like a clarifying question, or whether you want to wait till the end and reserve a few minutes. We'll just let you be in the driver's seat. And just a reminder to everyone to please hide your video when logging in. All right, take it over, Johan. Thanks.
Thank you for that very kind introduction. It's great to be here wherever here is. So MIT IDE sort of definitely is a focal point in the literature on understanding online experimentation, and Code is one of my favorite conferences. So it's great to be speaking sort of at MIT in this group off cycle on a more casual, sort of less frantic conference mode. So the work I'm going to be talking about today is recent work that was led by my Stanford PhD student, Hao Yin. Hao is wonderful. I would say, typically I'd be doing one of these pitches where I'd say, please hire Hao, but he's already been picked up and is off with a real job. The work was supported by the NSF, which I'm very grateful for. And let's get going. So the motivating problem that I'm going to be focusing on today is this challenge of you're trying to run an A/B test. And it's not your sort of vanilla A/B test where you have a bunch of people out in the world. You have a bunch of people whose experiences are interconnected. So there's at least two classic examples of this in my mind, in sort of particularly in the online domain. So the first is the situation where you have kind of, you're trying to A/B test some changes to sort of a feed algorithm. Some algorithm that whose behavior is really interconnected with the human behavior, and in particular with human social behavior. So you have a bunch of users of some online platform, and when I say sort of a feed algorithm, it can be something like Twitter or Facebook, but it can also be the types of, it can also be sort of search algorithms on sites like Airbnb, et cetera. And really what's going on is that you have sort of like in this little world, you have three users who are using this product, and you'd like to pair various performance metrics. In this world, so what would happen if you sort of gave all these users a brand new feed? Now, the problem is that all of their experiences of this product is highly interconnected. If you change somebody's feed algorithm, it changes how they interact with other users' content. And so you can't really glimpse both of these worlds at once. So it's really there's these two counterfactual worlds in the generic sense. There's sort of some network that's in its sort of gray mode steady state control condition. And you'd like to get glimpses of what would happen if you turned the whole network into sort of an upgraded version of a product or an algorithm change, et cetera. A third context, just to sort of put something on the table that's a very important application and has become increasingly important in the last few years, is this idea of understanding market algorithms, for the role of algorithms in markets, and being able to A/B test those types of changes. So consider something like a ride-sharing platform where you're making decisions on how to match individuals to cars. And so you have these individuals and there's sort of some sort of demand that they're providing to the market. And then we match cars to these individuals. But in another world, you might be interested in sort of asking, what happens if we change how we prioritize distance versus time, or prioritize the availability? Like maybe in this other algorithm, it's really important to be able to cover other parts of the map. So the problem there, just as in the feed algorithm setting, is that these two worlds are sort of really strongly counterfactual. You can't just get a little bit of a glimpse of sort of like, oh, what happens if we run, we'll assign this driver according to algorithm 1 and this driver according to algorithm 2. Oh, wait, they're trying to serve. So you have this sort of real difficulty that you can't easily get glimpses of sort of these two parallel worlds. So here's sort of another view of why A/B testing is hard. So in the absence of network effects, what's going on is that you have sort of all these units here. Sort of, we'll look at this one individual here. And if you give them the product upgrade, the green product, you're really getting, when they get the product, if there are no network effects, if it's really about their individual experience of the product, it doesn't matter what's going on in the rest of the network. They're going to sort of just respond to the fact that they have the product upgrade. So this is the sort of classic A/B testing scenario with Google changing the color or the font of their interface. These types of like interface changes that tend not to have social spillovers. Whereas in a setting where there are network effects, we're trying to ask ourselves, okay, how is this person that I just circled going to respond to the product upgrade? But they have the new feed algorithm, or they have the new video chat product, or the new X or the Y, but none of their friends, they only have one friend, none of their friends have this upgrade. They're sort of, their friends are still in the control condition. And so it's really this this problem that the technical term for understanding these spillover effects is whether or not you're willing to assume SUTVA, which is just a mouthful, and if history were different, it would have a better name, but it stands for the stable unit treatment value assumption. So think of it, the important part of the sentence is stable unit. The question is, are the units of the experiment kind of stable and not affected by various spillovers? So in the world without a network, you can really see there is sort of, you can make the stable unit treatment as value assumption, SUTVA, and say, yeah, that individual is behaving as if they were in treatment, or sorry, as if they're in treatment, and it really doesn't matter what else is going on in the network. In the presence of network effects, we really care about it. Sort of, this is not, what I'm circling here is not a reasonable approximation of that node's experience. If we look over here on the left-hand side, it's not as if it's not a representative view of what happens if you give everybody the product. Okay, so what approach are we going to take to this problem? There's a bunch of angles of attack. The main angle of attack that I'm going to talk about today is how to do sort of experimental design towards asking these questions about how to compare A and B. Sort of, if A and B are the two universes you're trying to compare, how can you design an experiment to give you as much power as possible, to give you as low variance and estimator of the difference as possible? And what are your tools? There are other angles of attack that I'll briefly allude to. It's turning into a richer toolkit by the day, by the month. So this approach that I've worked on since some work at Facebook together with colleagues there, Brian Carr, and then later Dean Eccles, who's at MIT, and then Lars Backstrom and John Kleinberg were also involved in the original work, is to essentially try and create glimpses, sort of portholes into both this A and this B world. So what you do is you cluster the graph using sort of graph clustering algorithms, which are, if you've never thought about graph clustering, it's sort of what it sounds like. You take a graph and you try and draw a circle around the nodes that are sort of strongly connected to each other. So you create a bunch of graph clusters, here only 2, and you treat the clusters with treatment, or the clusters with control. And the hope is, as sort of would luckily happen here for this example, we get this individual and we can start to reasonably feel as though this person is experiencing sort of the B world. On the other side, we can start to feel that this person up top is reasonably experiencing the A world, the control condition. And essentially by correlating the assignments of individuals, we've been able to get these glimpses of sort of like the full network on, full network off parallel worlds. So what I'm going to talk about today is a shortcoming with this method that has hobbled it, we'll say. And one simple trick goes very far, both in theory and simulation. And my pitch is that it can actually bring these types of methods sort of from marginally useful to really useful in practice. And I'm going to try to convince you of that via experimental design research is very tricky. So you have to sort of, you rely on theorems because it's so hard to run many experiments and establish the validity of one design over another. And then that's why we also rely on a lot of simulations. So this trick is, yay, my animation is working. So the trick is to basically say, instead of just considering a single clustering of the algorithm of the network, we're going to consider it's going to be a single clustering, but we're going to view it as coming from a world of clusterings that could have happened, sort of a bunch of random clusterings. And so our experimental design is going to be viewed as coming from this sort of distribution over clusterings. So we're going to pick one clustering and then use that. And the thing that we avoid is that with any given clustering, there are some nodes that get unlucky, and some nodes, many nodes get lucky and sort of get well surrounded, that node that we looked at. But if you focus on sort of one node through this blinking pattern, you'll see that sometimes it's sort of network surrounded, sometimes it's not network surrounded. And being able to sort of harness the fact that we have a decent chance of surrounding all nodes is kind of the key difference between regular graph cluster randomization and this idea of randomizing the clustering and doing randomization based on the random clustering. Okay, so we're going to talk about the experimental design toolkit for thinking about sort of how to correlate these assignments using graph clustering. I want to do a little bit more work to convince you, and not just clip art, that these are sort of important problems faced across sort of the big industry research teams.
John.
So
Johan,
if you look here,
Johan, can I just interrupt you for 1 second? And
please.
Johan, just to make sure that we all understand, because I think this is going to be crucial to the rest of the talk, the basic concept of the randomized graph clustering. Are you saying that essentially you're going to cluster the graph in a way that you believe is optimal, and then randomize the choices of assignment, or that somehow you're going to randomize the clustering and get a distribution over clusters first? It seems like you're saying the first, but I could be wrong.
Yeah, so I think actually I do mean the latter, but let me make sure that I mean what you mean. So the way that what I'm gonna argue for is, within a given clustering, there are certain nodes in this illustration, I'll sort of try and circle one, that got unlucky. They didn't get to be in the same cluster as all of their friends or the majority of their friends. They got a bad deal on what the clustering algorithm decided to do. So what we're going to do is, instead of just clustering once, we're going to cluster 1,000 times.
Okay.
We're going to cluster 1,000 times, and then we're going to sort of pick one of those uniformly, one of those clusterings, one of those ways to cut up the graph,
Yeah.
uniformly at random.
Okay.
And based on that one clustering that we picked, we're going to do our sort of like coin flips at the cluster level trick.
Okay.
But what's going to happen is that because you have a fair shot, because some nodes are going to get unlucky in that one clustering.
Yeah.
They're not going to have gotten a good deal. You know, a given clustering can't be fair to everyone. But if you have a lot of different clusterings, you have a fair shot of being well treated.
Yeah. Thanks.
And as we're going to compute these, we're going to look at these probabilities and show that like everyone has a much better chance of, you're not kind of like censoring your analysis because you've committed to one clustering.
And are you going to talk about the distributional property?
Oh yeah. Yeah.
Okay.
Yeah.
All right. Perfect.
Yeah.
Thank you. That's very helpful.
Yeah. No problem. Yeah, I usually try and sort of like give the 5-minute pitch so that people know whether they want to pay attention or not. But we're gonna go through in sort of full detail. Yeah. So this is just a simple slide to convince you that this is a real problem. So so Lyft deals with sort of the rideshare version of this problem. They have this blog post from 2016 about interference. DoorDash has been doing a bunch of work on switchback experiments. So this is another approach, which is where you're trying to solve this problem of all on, all off. And what you do is you go back and forth. There's some great work on this problem that I'll give references for later. Facebook, which is sort of a context that I've worked in the past, together with sort of a past collaborator, Brian Carr. They have a recent paper that's a great sort of like 2020 reference on sort of other bags of tricks to apply to these problems of estimating the difference between all on and all off. This is like a December 2020 archive paper on network experimentation. And then sort of an MIT joint, this is sort of paper out of David Holtz's thesis around reducing interference in pricing experiments at Airbnb. So this is sort of a generic or sort of widespread problem. I'm going to take a second to look at the chat because I see some problems here. I think somebody's helping me out with some answers. What's the difference in generating 1,000 clusterings and picking one at random versus just clustering once? Yeah, it's a good question. In the end, you're gonna end up with sort of the same coin flips. You're gonna get the same heads and tails. But the point is that you're gonna account for the fact that your clustering realization of how you clustered the graph isn't something that you should be conditioning on. It's something that itself happened at random. And some people got unlucky and some people got lucky. But I'm going to step through that in slower detail. Are there situations where a particular node cluster is it more important than others? Yes, certainly. So in a lot of marketplace experiments, you have whales. You have certain sort of accounts, sort of in ad markets. You have certain companies that do a lot of spend in ad markets. So there you have sort of two-sided markets, and you definitely have, you're not just going to focus on like average effects. You're going to be careful about that. You're going to care a lot about how your high value customers do. But that's a little bit orthogonal to sort of the motivating problem here. So in order to think about what effect these experimental design choices are going to have, let's look at this world that exists between everyone's in control and everyone's in treatment. So everyone's in control. We haven't introduced anything about our product. And then we start to introduce the product a little bit. And we're going to focus on sort of this situation where we have this node in the middle and sort of, things have started to happen in the big wide world, but actually they're still going to be considered in control because they're in control and all their friends are in control. So they are this like reasonable approximation to the network being fully in control. Now, here's where things there's a taxonomy of network effects that is richer than what I'm considering here. But we can look at things like the difference between the direct effect. So what happens if you get the product, which is sort of the top situation here, and the indirect effect, which is that there are certain product changes. It actually matters more what sort of in a social network, what your friends have than what you have. Think of this in a feed setting where, you know, in order, the main thing that drives your engagement with the site is like, is anybody interacting with your content? And if all of your friends have a really bad ranking algorithm that doesn't surface your content, then that's more important than like what your feed algorithm. If you're very production driven and the sort of like you live for the feedback on your own content production, that could be more important than what algorithm you're seeing if you're consumption driven. So the next stage is sort of that you're exposed and all your friends are exposed. Now there are steps in between this where like half your friends are exposed and other things are going on in the network. But once we've reached this condition, we've now securely given you the new product, given all your friends the product. We don't know what's happening on the rest of the network, but the main point of sort of this perspective is that we're going to sort of say that if you're exposed and your friends are exposed, that's almost as if everyone's exposed. If you're in control and all your friends are in control, it's almost as if you're in control. Now, the notion of friend can also extend to sort of competitor in these like marketplace type settings, or sort of like there's notions of adjacency other than friendship that you can apply to other contexts. So the question, I'm guessing you'll go over this later, but is the distribution over clustering well behaved? Yeah, so we're gonna define the distribution over clustering algorithmically because we want the properties of the clustering to be easily sampleable from. Yeah, we're gonna get there. So there's like great questions. So I just I wanted to have something that brought everybody into the talk, and then we're gonna get to sort of the meat that people seem to be craving. So this is great. Let's talk about the estimand, the thing that we're trying to estimate when we're looking at this control versus treatment. So consider the situation. So here's the vocabulary we're going to introduce. So we're going to introduce this vector z that's going to be sort of our main vector. And node I is treated if zi is 1. Node I is in control if zi is 0, right? So there's this 1 or 0. Great. So we have this whole vector z that's sort of a 0, 1 vector for all the units in our experiment. There's n units, so there's like 1,000, a million, a billion. And that's our global assignment vector. And now we're going to say that a unit has a response. We're going to say this is sort of this is the potential outcomes framework for those of you in the causal inference community. We're going to say that yi has a potential outcome for every possible z. And there's really like 2 z's that we care about. It's the z where everybody got 0, which is the global control, and the z where everybody got a 1. But in between, there's all these z's, and you know, you respond to a certain way when all the coins came up like so, and you respond in a different way when all the coins came up like C. There's sort of like, you have some sort of response that you give to every possible response. So the estimand, this effect that we're interested in, is what happens, what's the difference between the average across all the units of how they will respond to a global treatment versus a global control. Now, there's lots of really interesting work on heterogeneous treatment effects. We're gonna just look at the average. You could say that for those of you who are savvy to this literature, the global treatment effect need not be uniform. There might be a heterogeneous global treatment effect, right? Like certain people, the network effects are stronger for them than others. But we're going to focus on the average. This is sort of a higher level comment. And now this mouthful I introduced earlier, this sutva. Abdullah, did you have a question? You're welcome to jump in. Nope. Oh, sorry, I have my MIT code mug here. No, you're good? Okay. So what we're going to do is, here's a with this notation, here's what SUTFA can be, how SUTFA can be thought of. SUTFA makes the assumption that your response to any z is as if the world got the ones vector. If you and only you got a 1, doesn't matter what else is going on in the z vector. Your response to any z is as if to a global 0 if you got a 0. So this is SUTFA written in what's called an exposure modeling framework. And I'm going to talk more about sort of exposure modeling for the next, it's going to be kind of in focus for the next 3 minutes. And under this assumption, we have a very familiar estimand in causal inference, which is the average treatment effect, which is really like throwing away the network and just saying sort of like, what's y's response to the fact that zi is 1 and yi doesn't depend on anything else? What's i's response y when zi is 0 and I doesn't depend on anything else? And one thing to think about is that when SUTFA is true, when you have the stable human treatment value assumption, when there are no network effects, the gate is the 8. The gate is the 8. And so just keep that in mind, that like the gate is like an upgrade where you're like worried about network effects. If they're not there, it's the same thing as the average treatment effect. Direct exposure and indirect exposure are different or simultaneous strategy. So you're right. So this is a question from the chat. So the direct exposure is sort of, actually, I think yeah, perfect. Next slide. So what SUTFA does, and I'll respond to the comment in just a second, is it basically looks at the sort of all the things that could happen, and it sort of draws this dividing line and says like, I don't really care what else is going on in the network. I'm going to consider the situation here where somebody is totally surrounded by treatment. They're still in control. It's as if they're seeing the control world. The situation where on the top where somebody got the treatment but no one else did, we're going to sort of roll that all the way up to saying that they're experiencing sort of the product as if the whole world had the product. It's one of the things that I want to comment on is that I'm going to talk about experimental design ideas that are specifically targeting this like extremal difference between network control and network treatment. There are other experimental designs that are not necessarily just this clustering idea that you would want to use if your research question is about direct effects or indirect effects or distinguishing between direct effects and indirect effects. To give it, if that's like something that's top of mind for you, there's a section, it's either footnotes or in the appendix in the paper that Dean Eccles, Brian Carr, and I had about sort of a hole punching algorithm that tries to do something like graph clustering and move individuals over to the other side to try and put some individuals, increase the probability that people have these like isolated direct exposure or isolated indirect exposure experiences. It's a different estimand basically if you're trying to resolve those questions. And if you're trying to reduce the variance of a different estimand, it's reasonable that you would try and do other things. So that's sort of a very like specific comment to sort of understanding that we're really focusing on all off versus all on. Thank you, Dean, for the appendix pointer. So when we're looking at these exposure assumptions, we're really like throwing away the middle, and that's not necessarily the best thing to do in all cases. But we're gonna focus on, this is a really hard. This is my attempt to draw a star. This is a really hard thing to achieve. We can't see both the full network control and the full network exposure. So what we're gonna do is we're gonna focus on hoping that we get a lot of nodes sort of into this situation and this situation where they're kind of like locally exposed or neighborhood exposed or a neighborhood control. One thing I don't see here is the role of time. If network effects take time to diffuse, A is treated. Yeah, so time, that's great. There's a lot of the theory for these types of problems assumes sort of an immediate effect or an equilibrium effect. At the same time, in a lot of simulations, there's a dynamic involved, and that's really important. And the methods that are sort of unbiased when we talk about estimators and estimators being unbiased, it tends to be with respect to some kind of equilibrium. And if there's a dynamic involved, there can actually be biases. It's a great question. It's a hard question. A GCR variant for hole punching to estimate threshold effects. Good question. That's like a nice, it's a good goal to try and steer towards. I don't have one offhand, but I would think that you would want to do something like first cluster and then like vary what percent you hit the clusters with. But that's a great question, and Sinan, we should chat about that if you have an experiment in mind. Neighborhood exposure at this level of like, we're assuming that the people who are sort of locally treated are as if full treated and locally in control are as if full control. The formal language for this is that we're saying that I is responding to all the Z's as if it's the ones vector. If all the neighbors, if they and all their neighbors, so Ni is the neighbor set in kind of like graph theory notation, if Zj is 1 for all the J in the neighbor set. Similarly, we're going to say that they're in control, and we're going to assume that they're responding as if to a global control if all their neighbors are in control and they're in control. One question of time. Have you thought about randomizing on Ming clusters? That's a great question, and we're going to get back to why that's not necessarily the best idea. It's a great question. These situations of sort of like all my friends got treated, all my friends got control, we're going to define those, the set of all Z for which I has all of its friends in treatment. I'm going to declutter this. Is this event that I is sort of network exposed to treatment and I is network exposed to control. These are our two kind of events. You can think of them as subsets of all the Z vectors for which we're considered to be network treated, subsets of all the Z vectors for which we're considered to be network control. And then the estimand that we're looking at under this assumption is sort of this, this tau quantity that just takes the difference between the Y's for which Z is in. You'd like to know the difference between what happens when Z is sort of network treating I and when Z is network controlling I. Now these two quantities are counterfactual, but they're not as strongly counterfactual as sort of like the global treatment versus the global control. Question that came in, when are you measuring at a network level to know that you're effectively capturing the right activity? Knowing that you're effectively capturing the right activity is a great question. It's sort of a testing question, like whether or not Sutva is satisfied. There's a nice paper that I'll give a pointer to in a few slides. Martin Svesky and the team at LinkedIn were looking at testing whether there's a difference between a graph cluster randomized estimate and a non-graph cluster randomized estimate, which is sort of a way of testing Sutva. And then Dean Eccles, together with Susan Aithi and Hito Imbens, has this more specific paper on testing for spillover effects. There's another question here. I'm just enjoying all the questions. You'll probably talk about this when you describe the extremes. How does GCR play into the role of fake news and misinformation? Are there ways to figure out? Yeah, I'm going to table that. I haven't thought about how to kind of design experiments. You could ask about sort of like this, your understanding spillover effects between, well, here's an example. When you're running A/B, when you're A/B testing some kind of product intervention where you're like rolling out these information overlays where, you know, Facebook and Twitter are adding these little disclaimers or providing references to other things, those types of product changes have network effects. So trying to rigorously understand sort of like what happens when the whole network gets, because fake news spreads, trying to understand what happens on the network as a whole when everybody gets this product change is a hard one. So it is that's an example of sort of a product change that has strong network effects. And so you would want to, in an ideal world, be able to estimate the gate. And that's our goal. Okay, so this estimand is going to be sort of like our version of the gate, where we're going to focus on these people who are approximately treated and approximately controlled. And we have a pretty standard tool. In this talk, I'm going to focus on the Horwitz-Thompson estimator for this problem. And sort of for those of you who haven't seen the Horwitz-Thompson estimator, all you're really doing is, you couldn't observe the yi's in treatment and control at the same time. So what you do is you look at the ones that happen to come up network treated, you look at the ones that happen to come up network control, and then you divide by these probabilities. And the reason that you do this is that you can do a pretty simple, one of the sort of like the famous property of the Horwitz-Thompson estimator is that if you take an expectation, the only thing that's really random here is z. So what you're doing is you're taking an expectation of these two indicator variables, and the expectation of that indicator variable is its probability. So you get this kind of cancellation, and you have that the expected value of this Horwitz-Thompson estimator is the estimand that we want, tau. So that's why, that's what's great about the Horwitz-Thompson estimator. There are other ways to do it. There's sort of the Hayek estimator, regression estimators, both controlling for covariates and not. And I could say more about that. Sort of matching estimators. There's a whole literature on different estimators. But for the purposes of how we're going to optimize, or think about our design and optimize our design, what we're going to try and do is we're going to try and minimize the variance of the Horwitz-Thompson estimator. Other comments at this point, one of my favorite papers that I wasn't involved in, or I have a lot of favorite papers that I wasn't involved in, but I think Alex Chin's paper on regression controls and regression adjustment for interference is a great paper that has been underapplied. It comes up in this recent Facebook 2020 paper where they used regression controls quite extensively to get pretty far on estimating network effects. Alex's paper is actually under very simple experimental designs because he's sort of, his thesis, he was a statistics PhD student here at Stanford. He was one of my students, but this was independent work that he just knocked out of the park. And it's under very simple experimental designs. He doesn't look at it under things like graph cluster randomization. And he gets pretty far at being able to sort of identify and sort of control for network effects in kind of a regression controls framework. Here's 2 pointers on the switchback literature that's coming up. Switchbacking, I would argue that so there is somebody recently pointed out that the switchback literature started with like in agronomy with like cows, and they were switching between different ways to milk the cows, and cows are stateful. But there's for the purposes of online experimentation, there's this like in this recent sprint of literature that's really cool to see. Some questions that came in, what happens with the nodes that are half treated, half controlled? Yeah, so for my purposes and for the purposes of the theorems I'm going to give, they're dropped from the sample. In practice, you're going to want to do some modeling into the interior. You're going to want to say like, oh, I think that it's like the network effect like is proportional to the number of friends that were treated. And then you're going to, there are ways to do that. There's a paper out of LinkedIn that did that based on sort of a graph cluster approach. But for now, they're dropped, and the variance properties that I'm going to set up are assume that they're dropped. Did you consider spatial and temporal contiguity among the points in the network? Yeah, so a lot of the types of clustering algorithms that people use are spatial when you have a good spatial understanding of your nodes. So the thing that we need to do this type of estimation is we need to know these probabilities. That's important, and that's going to guide what types of experimental designs that we're going to consider. Okay, so this is the problem by now is set up. From now on, I'm going to talk about how do we randomize our graph cluster randomization, and what are the benefits of that. So just to summarize, so the gate is this global average treatment effect of an intervention, net of all the network effects, comparing these 2 parallel worlds. Exposure modeling is sort of a weaker form of SUTVA, where you're trying to look at things, you're trying to understand when somebody is sort of, when is somebody representative of the all on, all off condition. We can use sort of Horwitz-Thompson or Hayek estimators when the exposure probabilities are computable. I'm going to say what that, I'm going to spend more time on what that means for the remainder of the talk. And then here are some literature pointers. So a lot of this, so Aranon Samy, the first draft of this paper was out in 2011 when I was a PhD student and had a large influence on me. Mansky has this very sort of extensive treatment of different variations on sort of anonymous network effects, non-anonymous network effects, et cetera. Here's Alex's paper. This is a paper with Dean that came up that Dean pointed to Appendix A on. This is Martin Savesky's work at LinkedIn. Frederick Sevier has been doing some great theory of network experimentation. Okay, so now we're going to get into the meat. So consider the following 3 athletes for how we could run an experiment, how we could flip our coins. The base case is that we're going to do Bernoulli randomization. We're just going to flip all the coins, everybody's coin individually, sort of IID coin flips. You could do complete randomization, but that's not that important for the purposes of this talk. So everybody's getting an independent coin flip. And then GCR, we're going to cluster the graph once using a black box clustering algorithm. Somebody asked min-cut. You could do something like min-cut. There are reasons why you don't specifically want to do that. That is sort of an entire subsection of the RGCR paper. And then randomized GCR does this, yay animation approach where you do a random clustering and then you flip the coins at the cluster level. So this is a little bit back to Sinan's question to create one really obnoxious slide. You all feel like you're probably shopping for poker something right now. But in a Bernoulli randomization, all the coins are flipping independently. And like in any single realization, someone's going to be treated or controlled. In graph cluster randomization, you might start to see the problem that like you're always getting you're getting people network surrounded, but the same people in every sort of flip of the clusters, the same people are on the boundary. The same people are having a hard time. Whereas if you randomize how you did the clustering and then flip the coins, different people are well off and different people are poor off at different times. Now, there's this important point, which is that we need these probabilities to be computable. So that's something that we're now going to get back to. And that's arguably one of the reasons why I previously hadn't thought about randomized GCR. Okay, so just to be clear about what's so bad about independent coin flips when you're trying to estimate network effects. So the good news is that it's easy to tell when somebody is network treated if all the coin flips are independent, right? Because all I need is I needed this coin to come up heads, I needed this coin to come up heads, I needed this coin to come up heads. That's an easy computation. So that's not the problem. The problem is that these probabilities are often very small. If I have 20 friends, let alone 200 friends, it's really unlikely that all 200 coins came up heads. That's the problem, right? That's why we want to do these like cluster-based coin flips. You can't expect to ever get 200 coins to all come up heads. And if these probabilities are small, when the probabilities are small, the variance blows up and you have no reasonably confident estimate of the sort of global treatment effect. Nobody really got fully network treated. You might not even get anybody network treated, nobody network controlled. So let's see which parts of this problem GCR fixes and what it doesn't fix, and then we're going to randomize it. So given a fixed clustering, you can easily compute the probabilities. The good news is all you need to know is how many clusters a node is connected to. This red node is connected to only 2 clusters, the one it's in and one other cluster. So you just need, you sort of have independent coin flips at the cluster level. And that's great. So it's actually pretty easy to compute the probabilities. And you can actually compute the probabilities for more complicated notions of exposure that come up in the 2013 paper. And the good news is that it makes the event of sort of being network exposed to treatment or network exposed to control much more likely because you're in the same cluster as your neighbors. So the original kind of like result that I celebrated when we did the original GCR work was that because we can lower bound the probabilities of people being network exposed, because it's no longer sort of a really improbable event, you can upper bound this variance by a quantity that's not bad, but actually really bad. So it's not bad in the sense that, it goes down with n, and we're not sort of hugely dependent on the max degree of the network. So Dmax is the max degree. But we have this really bad term, which is that we have something, or so P is the probability of the flipping the coins. It's like a half. You're like flipping the clusters at probability P. So what does P to the minus kappa to the 6? Kappa is this property of the interference network. It's a graph property. And for now, theorists think of it as like 4. And so you have sort of 1/2 to the minus 4 to the 6, which is like 2 to the 4 to the 6, which is actually a really large number, turns out. So the theorem here is an asymptotic theorem that, like, when n gets large, we have an estimator that does pretty well, but the constants are atrocious. And so you can see this in the math that, like, GCR doesn't really deliver on a low variance promise because kappa is this constant. And the problem is kappa is not usually like 4. As we're going to see, it's usually like 100. So if you have 100 here, you're going to have your variance bound. And in fact, your variance, the bound has some slack in the analysis, but in fact, your variance is enormous. So here's the thing. You have this is the unlucky nodes intuition. So consider the fact that you ran the clustering on the left. This node V that we were going to focus on, it got really unlucky because it needed sort of 1, 2, 3, 4. Each color is a different clustering. 5 different clusters to all come up heads. Whereas had things been different over here, it would have just needed sort of one single cluster, one and done. So the idea of graph cluster randomization is to say, what happens if I randomize between these two randomizations? And then I can compute the probabilities of these events, which on the left is really improbable and on the right is really probable. And averaging tends to really shore up or sort of smooth out really, really small probabilities. Okay, so in deployment, we're only going to use one clustering. But what's going to happen is we're going to account for what could have been seen. We're going to account for all the other ways you could have been clustered. And the probabilities are easy to compute because it's just an averaging exercise. It's no harder than GCR. And there are sort of like, there's theory where you might want to study the distribution over clusterings. Improbable with unlucky. Okay, I'm going to address that question in a second. You're going to average across many runs. And essentially, if you cluster like 1,000 times, your probability of being treated, I need to like stop that animation somehow because it's distracting. You're averaging across many runs of the clustering, right? So instead of clustering once, you clustered 1,000 times. And instead of, in your specific realization of the clustering you used, somebody got unlucky, but that's okay, because what you're really concerned was their probability, sort of like, you're trying to equate them to people who are like them. And people who are like them have a certain probability of being network treated. And that's where you're trying to like control for, that's why you're using a Horvitz-Thompson estimator. And if they're the type of person who got unlucky and they sometimes get lucky, it's sort of not a big deal. This will be easier to see in some simulations. So let me say the last theoretical point, which is that in this new paper, when we choose a random clustering, and I switched the algorithm here, and I'm going to explain that algorithm for the remainder of the talk. Under this algorithm, we have the following variance bound. So the big difference is that when we were just doing GCR, we had this kappa to the sixth. So that kappa to the sixth is gone. We still have some dependencies that are significant, and those I'm going to try and convince you are sort of like not problematic constants, and also sort of like have a slack in the analysis. But the big difference that I want to highlight is this difference. Sort of, we had this quantity that was a gabillion, and we've been able to show that when we randomize the clustering, we're no longer dependent on this sort of kappa in this really, really, really bad way. You might say, for those of you who are like following along at this point, you'll notice that I'm talking about a new algorithm that I didn't talk about before. If you're reading the previous theorem carefully, yeah, 9 minutes, great. I'm gonna try and wrap up in like 6. We're talking about a new clustering algorithm. You might say, the previous work was under a different clustering algorithm. What if we just did GCR under the new algorithm? We actually get sort of a, this trade-off of we replaced kappa with Dmax. So both of these are bad. Like GCR is not good. This algorithm is just particularly good when you're doing it in a randomized way. So what's the algorithm? Okay, what is kappa? I need to explain what kappa is before I can convince you that it's problematic. Basically, kappa is, it's called the restricted growth rate of a network. And it's this ratio of sort of how much the ball size of different neighborhoods blow up from step to step. So it's this bound on, if you have 100 people in your 2 ball and you have 1,000 people in your 3 ball, then kappa becomes 10. It's this sort of like, it's the explosion factor as you go out from all the nodes, but it's worst case. So it's a kappa, it's the smallest kappa, such that at every radius on every node, you never get a blow up factor greater than kappa. Now, it comes from this literature on bounded geometries in sort of like math and theoretical computer science, but there's actually been a bunch of parallel work on using growth assumptions in network interference experiments. See these 2 recent papers that are in the bibliography of the randomized graph clustering paper. The point is that theorists think of kappa as 4, and one of the sort of empirical contributions we have in the randomized in this new paper with How, because How is sort of a amazing computer, we pushed all the Facebook college networks through a bunch of graph computations. And when you look at these college networks, these are networks that are, between 1,000 and 30,000 nodes, and their kappas are like 100. They're not 4. They're not even 10. They're like 100. So any type of like result that leans heavily on like the network doesn't grow that badly needs to contend with the fact that kappa is actually like a really big number on networks. So the important thing here was that the fact that we had this kappa to the 6 that's no longer in the exponent. And we also shaved a kappa here, but that's sort of details. Okay, so how are we gonna, what is this clustering algorithm that I'm advocating for? If you know the graph cluster randomization work, you know that in theory, there's an algorithm there called 3-net clustering. Here's a simpler algorithm that was much more analyzable than 3-net, and it sort of was How's innovation when we were studying this problem. Is he was having a lot of problems analyzing the 3-net algorithm, and he found that the following algorithm works really well, and it turns out to be, it has a prehistory in the literature that we cite and give pointers to if you know your FRT algorithms and things like that. But for every node, sample a uniform number on 0, 1, and then take the max of the neighbors. So if we have everybody sampling a uniform number, everybody takes their max, and then you cluster according to the max. So this is all the one-hop max algorithm does. It's super simple. Everybody takes a random number, take the max of the neighbors, and basically if you got a really high number, you won all of your neighbors and you get a cluster out of that. It has practical similarities to 3-net, but it's a lot easier to analyze, and it's also really easy to compute. there are some important results. So the clusters are low radius, which is useful for being able to do distributed computation. Everyone has a chance of at least 1/n of being network exposed, of being neighborhood exposed. That's pretty useful. Essentially, because you're randomly clustering the algorithm, anybody could get the highest number. And if you get the highest number, you win all of your neighbors over to your cluster. And that's one of the main things that, like, under a fixed clustering, somebody could get unlucky. But if you randomize the clustering, everybody has a fair shot of being like really network treated or really network control. Advanced material, you can sort of like do a weighted version of this that I'm gonna skip over. And here's the retrospective magic trick for RGCR. So I mentioned that in the end, you only use one clustering. You know, you create 1,000 and then you use one of them. There's an important thing here that you didn't actually need to create 1,000. You just needed to create one to run the experiment, and the other 999 were just for the purposes of like computing the treatment probabilities. So you can actually just create one and then create many, many more when you're doing your analysis later. So that's great that like you don't need to create 1,000 or 10,000 clusterings up front. And the other thing is, if you, as some people in the audience might have done this, if you've run a GCR experiment using a fixed clustering from something that's inherently a randomized clustering algorithm. So 3NET is a randomized clustering algorithm. Most algorithms have some randomized tie-breaking element in them. If you've done this, you can legitimately replace your exposure probabilities with, under GCR, with RGCR probabilities. And basically, you're just going to take an expectation over many runs of the clustering algorithm and see how things would be differently and get new probabilities that are much, much, much better behaved. So here's sort of this unicorn indicating that this is really a magic trick that, you know, if you were lucky enough to have had a randomized algorithm in mind, you didn't need to suffer from the fact that you had a bad outcome on that algorithm. Does this, Dave says, does this mean that there are certain clustering algorithms that do a worse job of producing good results? Yeah. That's one of the nice things about one-hop is that it's the different clusterings. If you do it 1,000 times, it's very different across the 1,000 times. So Dave says, less random than one-hop. Yeah, so that's why you don't want to run just like a massive like min-cut algorithm. I'm out of time. So I'm just going to say that there's these simulations where the variance goes down. I wanted to deliver the intuition most of all, but essentially we analyze both sort of 3NET and one-hop. As you consider more and more clusters, you go from these huge variances, which is GCR, down to these tiny variances, which is RGCR. So the left-hand side here is GCR, and then you're considering mixing more and more clusters. And that's great. It turns out that there's many variations that don't really change things, and the exposure probabilities are small.
Sorry, Johan, can you just go back?
Yeah.
And just a quick question, right? One more,
yeah.
right here. I thought K was the explosion factor. Can you explain why GCR is?
Yeah, sorry, that's a good bad choice of K, because K and kappa are different.
Oh, it's
so kappa. Yeah, kappa is this like graph property. Yeah. And here I'm using K to just say how many clusters I'm mixing across. And so if you look at something like one-hop max, if you're just doing GCR, meaning you're not mixing, you have this really high variance.
Yeah.
But then as soon as you're mixing over 10 clusters, over 100 clusters, over 1,000, over 10,000,
yeah,
your variance starts to be, and the question, so there's a separate question, which is like, how many clusters should I average over? This dashed line, this vertical dashed line is N. It's like the size of the network.
Okay.
And so as long as you have, what's happening is once you're like past N, everybody's had a fair shot of being first in like the random one-hop max situation. So if you're averaging across the situation, or actually you need N log N, but like roughly speaking, everyone's had a chance of being first. So you don't need like 1 trillion clusterings, you need like a factor more than N.
Okay.
And that's when you plateau down to these low variances that RGCR can achieve.
Awesome.
And then here is sort of like the scales are much better here, where you're like down to like real integers.
This is great.
Yeah, I'm gonna wrap up. The gates is important estimand. RGCR does this thing where it smooths things out. How is a hero? He spent like a year in the trenches wrestling a lot of details of this work. The paper is on the archive.
Awesome. Johan, this is fantastic. This is really, really important for people who are in this stuff. To see this is great. I will be I will publicly out a text message exchange that I'm having with Dave Holtz while we're listening to you, where he's saying, where I say, you know, the HT estimator wasn't all that productive on VAR in the original. And he says, yeah, it's funny to be watching this while we have 50 cores on equity running GCR simulations. Calculating the variance on that HT estimator is very gross. So we truly appreciate all the work that
If you want to
guys
reach out, I'm happy to like tease apart what something y'all might be facing. Yeah, for sure.
Yeah. By the way, I will say, and I have to ask this because I don't know when I would be able to get you on the phone. The fact that Kappa is 100 plus up to 3,000, I think that has massive other implications that have nothing to do with networked experimentation. I would be very interested to think about the implications of that for lots of other things
there's right. It's actually this like interesting descriptive finding that's closely tied to everything from like degrees of separation to other things, right? Because it's about like, so to be clear, as a number, it's driven by people who have a low degree who have a lot of friends of friends.
Right.
It's the fact that like you have like a degree 5 and then the one of the 5 people is this super high degree person.
Yeah.
But that's this like structural property that I haven't seen analyzed much in this literature that's looked at things like degrees of separation, et cetera. And I think there's a whole descriptive paper to write.
Yeah. Oh, I thought you were gonna say there was one, and I was gonna say send it.
Yeah. No.
On that point, I would wonder though whether that worst case bound is the best summary or not. For some things, it seems like it potentially is, right? But for other things, maybe it's not. I mean, I can see how, even for
one of the reasons
or seeding, it could be useful. If there's somebody who has very low degree, they don't realize they're influential, but in fact, you know, they're not so far away. But oh, you have averages here. I see.
Yeah, so we look at the average number of nodes.
Let me stop you guys for 1 second. Let me stop you guys for 1 second because I feel like we're about to geek out, and I really would like to get to that immediately. But for everybody else here who just wants to go have their lunch, let me just say thank you very much to Johan for a fantastic presentation, and to remind everybody that next week we have Tim Huang, who's going to talk about the subprime attention crisis in online advertising. So be sure to tune into that next week, same time, same bat channel. Okay.